Bismillahirrahmanirrahim. Assalamu alaikum. In this lecture, we shall study the concept of maxima and minima. The greatest value or the maximum value of a function is called maxima, and the smallest value or the minimum value of a function is called minima. If we are given a function f of x which is defined in a closed interval a comma b, and if there exists a point c1 in this interval such that f of x is less than or equal to f of c1 for all x belongs to this interval, then we say that f of x has absolute maximum value at that point x is equal to c1, and f of c1 will be the maximum value. Similarly, if there exists another point c2 in the interval a comma b such that f of x is greater than or equal to f of c2 for all x belongs to that interval, then we say that f of x has absolute minimum value at the point x is equal to c2, and f of c2 is the minimum value. Let us see the graph of a function. This one is x-axis and this one is y-axis, and let us say this is the graph of some function f of x which is defined in the interval a comma b. Now let us say we have a point c1 here, and this value is f of c1. So we can see that f of c1 is greater than, or any other value f of x is less than or equal to f of c1 for all x belongs to the interval a comma b. So that is why f of c1 is the maximum value. And now let us draw another line here and say this is c2. So this value is now f of c2, and we can see that f of x is greater than or equal to f of c2 for all x belongs to that closed interval a comma b. In other words, if I take any value from this interval a comma b and put that value in the function f of x, I can get that f of x is greater than or equal to f of c2. So f of c2 is the minimum value of that function. Let us see the method to find the absolute maximum and the absolute minimum value of a function on a closed interval a comma b. If we are given a function f of x which is defined on some closed interval a comma b, the first task is that to find its critical point. So differentiate the function and put f dash of x equal to 0. From here, we can find the critical points. Let us say C1 and C2 are two critical points. Then put C1 in the given function and obtain its value. Put C2 in the given function, obtain its value. Put point A in the given function and obtain its value. Put B in the given function and obtain its value. Now the largest value in these four will be the absolute maximum value of the given function f of x. And the smallest value in these four will be the minimum absolute value of the function f of x in the given closed interval. Let us see it graphically. So we draw the graph of the function f of x between a and b. Now the point at which the tangent become parallel to the x-axis, f dash must be 0 at that point. So this one is the critical point. And another critical point at which the tangent becomes parallel to the x-axis, derivative of the function must be 0 at that point. So we have two critical points. Let us say this one is C1, this one is C2. Now we have to find the distance f of A, then f of C1, f of C2. Similarly, we can find the distance f of B. The largest in these four will be our maximum value, and the smallest in these four will be our minimum value in the given interval a comma b. To explain the method, let us find the absolute maximum and minimum values of this function in the interval -4, 1. The first task is to differentiate the function. F dash of x is equal to -2 minus 2x. To find the critical points, we put f dash of x equal to 0. And from here we get -2 minus 2x is equal to 0, which gives -2x is equal to 2. And we have only one critical point, which is -1. Now let us put -1 in the given function f of x. So f of -1 is equal to 1 minus 2 into -1 minus into -1 square. From this we get 1 plus 2 minus 1. So f of -1 is equal to 2. Now let us put x is equal to -4 in the given function. So we have f of -4 is equal to 1 minus 2 into -4 minus -4 whole square. If we simplify, we get 1 plus 8 minus 16. And from this we get that this is equal to -7. The last point is x is equal to 1. So let us put it in the given function. We have f of 1, which is equal to 1 minus 2 into 1 minus 1 square. If I simplify this, we get f of 1 is equal to -2. So we have three values now. F of 1 is -2, f of -1 is 2, f of -4 is -7. So in these three values, the smallest value is -1. So we can say, therefore, f of -4, which is equal to -7, is the absolute minimum value of the given function f of x. And we can see that f of -1 is equal to 2 is the greatest value. Therefore, we can say f of -1, which is equal to 2, is the absolute maximum value of the given function f of x. In example 2, we are given f of x is equal to log x over x, and we have to find its maximum and minimum values on the closed interval 1, 3. So let us differentiate this function. F dash of x is equal to, we use the quotient rule. So according to this rule, we write the denominator square. So we have x square, then x differentiation of log x, which is 1 over x, minus log x and differentiation of x, which is 1. So we have 1 minus log x divided by x square. To find the stationary points, let us put f dash of x equal to 0. And from here, we get 1 minus log x is equal to 0, which gives log x is equal to 1. And this will give us the first critical point, x is equal to e, because log e is equal to 1. Now, in the next step, let us put x is equal to e in the given function. So we have f of e, which is equal to ln e divided by e. Log e is 1. So we have 1 over e, because the value of log e is 1. And if we use calculator, we have f of e is equal to 0.367. So this is the first value. And now let us put x is equal to 1 in the given function. So we have f of 1, which is equal to log 1 divided by 1. And this is equal to 0, because log 1 is equal to 0. So we have the second value, f of 1 is equal to 0. And now let us put the next point, which is x is equal to 3 in the given function. So we have f of 3 is equal to ln 3 divided by 3. And if we use calculator and find its value, we have f of 3 is equal to 0.366. This is the value of f of 3. Now we can see from these three values that f of e is the maximum value and f of 1 is the minimum value in these three. Therefore, we will write f of e is equal to 0.367 is the absolute maximum value at the point x is equal to e. And similarly, we can write f of 1, which is equal to 0, is the absolute minimum value of the function f of x at x is equal to 1. Local maxima and minima. To find the maximum and minimum value of a function f of x on a whole real line, are on the whole closed interval, then that type of maximum and minimum values are called the absolute or global maximum and minimum values. If we find the maximum and minimum values not on the whole real line or not on the whole closed interval, only in some small open interval, then those types of maximum and minimum values are called the local maximum and minimum values. We find the local maxima and minima by using two famous tests, the first derivative test and the second derivative test. So let us explain the first derivative test to find the maximum and minimum values of a function f of x. Let us explain the first derivative test by the graph of some function f of x. So I draw the graph of some function of a function f of x. Now the first task is to find the critical points. So at the critical point, f dash must be equal to 0 because the tangent must be parallel to the horizontal axis. And we can see, let us, that is point C, which is the critical point. Now look at the graph. Before C, the graph is increasing. It means f dash is positive. And after C, we can see that the graph is decreasing. So f dash is negative. That is why the first derivative test says that f dash changes sign from positive to negative. This will imply that f of x has a local maximum value at that point. And now let us draw another critical point, which is here. And we can see that the graph is parallel to the x-axis. So f dash is 0 at that point. But we can see that before that point C, the graph is decreasing. So f dash is negative. And after that point C, the graph is increasing. So f dash is positive. That is why the first derivative test says that if f dash changes sign from negative to positive, this will imply that f has a local minimum value at that point C. Now let us see the definition. The first task is that to find the critical point of the given function f of x, which is C. Now represent that point C on a real line. Now before C, on the left hand side, we have numbers which are less than C, and on the right hand side we have numbers which are greater than C. So put a number which is a little less than C in f dash and look at the sign if it is positive. Then put a number which is a little greater than C. Put that number in f dash and again look at the sign. If the sign of f dash changes from positive to negative, it means that f of x has a local maximum value at that point. Now look at again another real line and represent a point C at that line. Again repeat that procedure. put a point which is lesser than C in the given f dash and look at the sign if it is negative. Now put a little greater number than C in f dash and look at the sign if it is positive. We will say that f dash changes sign from negative to positive, and hence f of x has a local minimum value at that point. Then the third point says if f dash does not change sign at C, then f of x has no maximum or minimum value at that point. In example number 3, we use the first derivative test to find the maximum and minimum values. So the first task is to differentiate this function. Let us find f dash of x. So f dash of x is equal to x square minus 3x plus 2. And now let us factorize this. So f dash of x is equal to x square minus 2x minus x plus 2. And from this we get x into x minus 2. Taking minus 1 common, we have x minus 2. So f dash of x is equal to x minus 1 into x minus 2. Let us say this is our equation number 2. Now for the critical point, we put f dash of x equal to 0, which means x minus 1 into x minus 2 is equal to 0. From this we have two critical points, x is equal to 1 and x is equal to 2. And now we have to find the local maxima and minima at these 2 points. Let us consider the first point, x is equal to 1. So we must indicate that number on a real line. Let us say this is 1. Then we know that on the left hand side we have 0, on the right hand side we have 2, and so on. So we must take a number lesser than 1, which is very near to 1. So very near to 1, we can take 0.9. And then we need a number which is a little greater than 1. So that number is 1.1. And we will check the sign of f dash on these two numbers. So let us find the sign of f dash on 0.9, which is equal to 0.9 minus 1 into 0.9 minus 2. And if we simplify this, after simplification, we can get that this is equal to 0.11, which is a positive number. And now let us find the sign of f dash on the number 1.1. So let us put that number in 2. We have 1.1 minus 1 into 1.1 minus 2. And if we simplify this, we get minus 0.09. So we can see from these two values that f dash of x changes sign from positive to negative. And this implies that f of x has maximum value at x is equal to 1. And to find the maximum value, now we can put x is equal to 1 in equation number 1. So we have f of 1, which is equal to 1 cube divided by 3 minus 3 into 1 square divided by 2 plus 2 into 1. And if we simplify this, we get 5 by 9, 5 by 6. And that is the maximum value. 8, x is equal to 1. Now let us see the nature of the function at the next critical point, x is equal to 2. We will repeat the same procedure. Let us indicate 2 on the real line. So on the left hand side we have 1, 0 and so on. On the right hand side we have 3, 4 and so on. So we need a number which is a little less than 2 but very near to 2. So that number is 1.9. And we need another number which is greater than 2 but very near to 2. So that number is 2.1. And now let us see the sign of f dash at 1.9. So we have 1.9 minus 1 into 1.9 minus 2. And if we simplify this, we have minus 0.09. So we have a negative number. And now let us find the sign of f dash at the number 2.1, which is equal to 2.1 minus 1, 2.1 minus 2. And if we simplify this, we have 0.11, which is positive. So we can see that f dash of x changes sign from negative to positive. So this implies, according to the first derivative test, f of x has minimum value at x is equal to 2. And to find the minimum value, now we can put x is equal to 2 and 1. So 1 implies f of 2, which is equal to 2 cube divided by 3 minus 3 into 2 square divided by 2 plus 2 into 2. And if we simplify this, we get that this is equal to 2 by 3. And that is the minimum value of f of x at x is equal to 2. The second derivative test is easy than the first derivative test. As usual, we find the critical point C, and now we put that point in f double dash of x. And if f double dash of C is less than 0, it means if f double dash of C is equal to some negative number, then the function f of x has a local maximum value at that point. And if we put C in f double dash of x and f double dash of C is greater than 0, in other words, if f double dash of C is equal to some positive number, in that case we say f of x has a local minimum value at x is equal to C. The last point is that if f double dash of C is equal to 0, this test will be failed, and we will go to the first derivative test. In example number 4, we use the second derivative test to find the local maximum and minimum values. So as usual, let us differentiate this function. So we have f dash of x is equal to 3x square minus 6x, and for the stationary point, let us put f dash of x equal to 0. From here we get 3x square minus 6 is equal to 0. And now we take 3x as a common. So we have x minus 2 is equal to 0. From this we get two stationary points. X is equal to 0 and x is equal to 2. And now let us use the second derivative test to find the nature of f of x at these 2 points. So let us say this is equation number 2. We differentiate 2 once again. So we have f double dash of x, which is equal to 6x minus 6. And now let us put the first point, which is x is equal to 0 in f double dash. So f double dash of 0 is equal to minus 6, which is less than 0. In other words, this is a negative number. So this implies that f of x has a local maximum value at x is equal to 0. And now let us find the maximum value. So we must put x is equal to 0 and 1. So the maximum value is f of 0, which is equal to 3. So 3 is the maximum value of f of x at x is equal to 0. And now let us check the second point, x is equal to 2. So again we put x is equal to 2 and f double dash of x. So we have 6 into 2 minus 6, which is 12 minus 6 is 6. And we can see this is greater than 0. In other words, we can see that this is a positive number. So according to the second derivative test, we say f of x has a local minimum value at x is equal to 2. And now to find the minimum value again, we put x is equal to 2 in the given function. So f of 2 is equal to 2 cube minus 3 into 2 square plus 3. And if we simplify this, we have f of 2, which is equal to 2. So f of 2 is equal to 2 is the local minimum value of f of x at x is equal to 2. That's all.